Hello, everyone. I am Martin Szyld from Dalhousie University, and in this talk, I will present the results of an article with this same name, Lifting Pi Limits with Strict Projections. I thank the organizers for this opportunity to present my work, and I thank you for watching. As a quick overview of the talk, I have 6 slides. In the first 3, I recall some notions and results about lifting limits in two-dimensional monad theory, and in the last 3, I present the results of this article. I will start by recalling the context of the article Two-Dimensional Monad Theory by Blackwell, Kelly, and Power, and what it means to have a lifting of a limit here. So we consider a two-category K and the two-monad T on it. We are then given this two-functor over line F into a two-category of T algebras. We denote by F its composition with the forgetful two-functor U. And we ask the question of when we can lift its limit, the limit of F, from K to this two-category. So what we want to do is to give the limit of F an action of T, such that this T algebra becomes the limit. Now, it's been noted since then that this question becomes harder, or at least that we seem to be able to lift less limits when we relax more and more the algebra morphisms. To clarify this, let me recall that one can consider lax morphisms between T algebras, where instead of asking for the equality of this diagram, we put a two-cell in it. If we ask for this two-cell to be invertible, we call that a pseudomorphism, and if we ask for it to be an identity, that's a strict morphism. There is quite a history of limit lifting results of this kind, but I won't go into the details here for lack of time. In this second slide, I want to tell you the basic technique for lifting these limits. I will illustrate this by lifting op-lax limits to the two-category of algebras with lax morphisms. I will probably forget to say the word op a few times, so just remember this instead. The two-cell should go upwards when the arrow goes downwards. So an op-lax cone is like a one cone, but with these structural two cells instead of equalities, one for each arrow in the indexing two category A. And an op-lax limit is a universal op-lax cone, which for the purpose of this talk will mean that any other op-lax cone factors uniquely through it, just like a one limit. Now remember from the previous slide that we lift a limit L to T-alg by giving it a T-algebra structure that is an action of T. And the main point of this slide is that we do that by defining an op-lax cone like this. We paste these two cells coming from the involved structures, the one on the right from the lax morphism and the one on the left from the universal op-lax cone. So we get this L, the desired action of T on L by the universal property of the limit. Note that these two squares commute strictly, and that means that the projections of the original limit become strict algebra morphisms. All right, so in this third slide, I want to introduce sigma S limits that actually go back to the 70s, but that we rediscovered in a different situation in a project with Eduardo Dubuc and Emilia Descott, and this article. And since then, we believe that they deserve a bit more attention, and we hope that they continue to get more and more attention in higher category theory. This kind of has already started, and we hope it continues. So we fix a family of arrows of a two category. We call those the marked arrows, and we consider only the lax cones, such that these structural two cells are identities when F is marked. Remember, there was one of these two cells for each arrow in A. So now we ask some of them to be identities. A sigma S limit is, of course, a universal sigma S cone. Any other sigma S cone factors uniquely through it. Now, as you see, in a sense, these guys are almost as simple to introduce as conical lax limits, but they are as expressive as weighted two limits. And this also goes back to the 70s. I won't go into the details here, but keep that in mind. For any weighted two limit, there is a sigma S limit with the same universal property. Okay, so finally starting with some new content, the first thing I do in this article is play the game of sigma S pi limits. Recall that pi limits are those that can be constructed from products, inserters, and equifiers. So in other words, I look at which sigma S limits are so. Here is the answer, which wasn't really hard to guess by looking at this 91 article. You want the connected components of the category given by the marked arrows to each have an initial object. Then I show, much like one limits can be constructed from products and equalizers, that you can construct all pi limits from these three basic ones. I only want to look here with some detail at the inserter because I think this is an instructive example. Note that a lax cone for the inserter has all this data, but now since f is in sigma, we are asking that theta f is an identity, which means that theta f is this composition here. Sorry, so we get that only theta a and theta c are the actual data in the cone, which is, as we expected, the data for an inserter cone, an arrow into f of a, and a double cell, just like this. So the idea or the intuition for pi limits and pi indexing pairs is that this is what always happens. In each connected component, you have an initial object, in this case A, and only one marked arrow from it to the other objects. So the only real projections are the ones corresponding to these objects, and the other ones are given by composing with the images of the marked arrows. These real projections play an important role in our limit lifting result. Now, I mentioned before that any weighted limit can be seen as a sigma S limit, but I want to emphasize here that when you do that to the weighted inserter, then you get a different presentation of this same limit. It will have three objects and two marked arrows. Okay, so the reason I looked at pi limits like that was to lift them to the algebras, and we will do that now. Here is the trick. Remember that we had a diagram like this, and we wanted to lift the limit of f. So, and now we want to lift a sigma s limit of f, and we have marked some arrows, sigma of a, such that this is a pi limit. So we have these initial objects that we denote here like that. For each a, we denote a0, the initial object, and we denote fa, this unique arrow from it into a. I'm hoping you remember that to lift Oplak's limits, we built an Oplak's cone, theta, with this pasting. Now, this Oplak's cone will not be a sigma S cone like we want now, because these won't be identities in general. But the trick is to modify it like this. As you can see, we paste the structure that's coming from the initial objects for A and for B. Note that this two cell in red below is an inverse. It goes in the same direction that the arrow, not in the opposite direction, like for lax morphisms. Now, why will this be a sigma S cone? Well, when the arrow F is in sigma, then A and B are in the same component, in the same sigma component. So the initial object is just one. And since there is only one marked arrow from it into B, it has to match the composition of F with FA. So this right part here becomes an identity. These two triangles always commute. And when F is in sigma, so does this one, precisely because pi was a sigma S cone. So that's why this works. So in this final slide, I just state the theorem, whose proof after using this trick becomes more or less routine checks. Note the red hypothesis coming from the red two cell in the previous slide. And note that the projections that are seen to be strict and strict preserving are the ones corresponding to these initial objects. Like I mentioned before, when we looked at the inserter, the only real projections for a pi limit. I'm putting here this version of the theorem, which is about lax morphisms of algebras, so the worst possible situation in a sense, but it also holds for pseudo and strict morphisms. Now, in this case, the red hypothesis becomes trivial. All these two cells are invertible. And this lifting result for pi limits was known in this case, but these projections hadn't been identified. So, for example, in the two-dimensional monad theory article, they had to show this result once for each of the pi limits they wanted to lift and use the explicit construction of such a limit from products, inserters, and equifiers. Here we take care of all pi limits at once. Now, for lack of time, I won't say much more on this here. Instead, in these final seconds, I want to look at the red hypothesis for the example of the inserter. Note that if we take this inserter, the one we looked at a few slides ago, then the red hypothesis will be asking for one two cell to be invertible, which is the correct hypothesis for lifting an inserter. But if we want to use the weighted inserter, then this doesn't work, because remember that now 2 arrows are marked. So we will ask for a stronger hypothesis, which is not the correct one. We need to consider true sigma limits, which are not the ones coming from weighted limits with the elements construction of the weight, to get the correct lifting result. Thank you very much for your attention, and here are some references.